Hello class, this is CSE-5250, sections 2 and 60, week 7, spring 2026. I'm Giovanni Orijuela, and let's talk about the trapezoid rule, the trapezoidal rule. So this is something that's taught in the introductory portions of integral calculus, where you have the area, you have to find the area under a curve, and to get started, you would just divide that area into a series of either rectangles or trapezoids, depending on which method you're using. In this case, we're going with trapezoids because, well, it's intuitively it would be a lot more accurate than doing this with rectangles. But doesn't matter which method you use, it all ends up being the same in the end when we crank up the trapezoid count all the way to infinity. Or more formally, you have these trapezoids. They're all the same width, and as we increase the number of trapezoids, as that quantity approaches n, the quantity of trapezoids is, of course, going to approach infinity, but the width of the trapezoid is also going to approach 0. And once we have this summation, well, we have the limit of this summation here, where f of x sub k minus 1 and f of x sub k, those are the two endpoints of any one trapezoid. And that is actually the area of a trapezoid formula, where you have a trapezoid and it has two different heights. Call it h1 and h2. You average those two heights so that you effectively turn that trapezoid into a rectangle. So it's going to be height 1 plus height 2 and then all over 2. That's literally the average height of those two different heights. And then you multiply it by the width of a single trapezoid, which in this case is going to be delta x sub k. But how many trapezoids do we have? Well, we have n trapezoids. So it's going to be a summation of this from k equals 1 to k equals n. Also, it might be a little bit, of course, it's going to be the case where the width of every trapezoid is going to be the same, so that delta x is going to be the same all the time. So, but the thing about calculus is, once we're gonna increase n such that as n approaches infinity, we can then finally say that the right hand side as n approaches infinity is going to perfectly equal the left hand side. And that's literally how the integral is defined. But we're not doing anything infinite here. We are rather doing an approximation by cutting up the area into a finite number of trapezoids. Because if we did this to infinity, we'd literally be here forever. So, let's think about how we would want to implement this as a computer program. Though, we already have the code right here. That's a little bit confusing because h in here, in this code, h is the width of a trapezoid. So, how do we find the area of any one trapezoid? Well, we could just do the trapezoid area formula over and over and over again for each trapezoid you have, but you'll notice that this code is a little bit simplified. Let me explain. So, if we did just that, where we find the area of each trapezoid, and keep in mind, the area of a trapezoid is, well, as I said, the h in this case is supposed to be the height, but it's used to represent the width of a single trapezoid. So f of a1 and f of a2, those are the heights. Those are supposed to be the heights of one single trapezoid, but I guess they're the widths now. Anyway, we have h, which really should be the width, and the two heights. That's literally the area of a trapezoid, and we're just doing this over and over and over and over again until we have all the trapezoids. And it's the sum of all these trapezoids that gives us the area under the curve, or at least an approximation of the area under the curve. But put in your mathematician's hats for just a moment, and notice that every term in the summation is literally being multiplied by h. So you can just simplify it to h, and then in parentheses, everything else. But also notice that we have f of a1 and then f of a2. Technically that a should be an x if I had to follow the notation, but so just pretend the a should be x's. Anyway, a1 and a2 are the widths, or rather the heights of the first trapezoid. a2 and a3 are the heights of the next trapezoid after that. a3 and a4 are the heights of the next trapezoid after that. So on and so forth until we get to an minus 1 and then an. But we can distribute the divide by 2 such that we have f of a1 divided by 2 plus f of a2 divided by 2 plus f of a2 divided by 2 plus f of a3 divided by 2, and so on and so forth. But you'll notice a pattern. We have 2 f of a2 is here, 2 f of a3 is here. There would be 2 f of a4s here, so I'll just draw it like this. And then there would be 2 f of an minus 1s here, so I'll just draw it like that. So the fact there are 2 of them just means that we just cancel out the 2's and cross out the extra term here. So I'll just do that. I can't cross these out because they're hidden, but at the end we should have basically h times the quantity f of a1 over 2 plus f of a2 plus f of a3 plus f of a4, and so on and so forth to f of a minus 1, and then f of an over 2. And we can rearrange this even further by saying the initial area. We're just gonna assign that. We're just gonna say the area is f of a1 plus f of an divided by 2 plus f of a2. Well, I have to put the... Hold on. I'll just write it like this. So we have this fraction here plus this summation here. Oh yeah, and everything, this whole thing is multiplied by h. So you have the summation here. Well, we have this fraction here, and then the summation here. And this summation is adding a trapezoid after one and after another. One after another, after another, and after another. In code, that's basically a for loop right there. And then this part, we can just set the initial area to be just this portion. And then after that, we can just do a for loop in which we just add f of a2, and then f of a3, and then f of a4, one after another. So that's what's going on in this code here. So let me just turn back on the slideshow. Wrong one. Let's go back to the slide. So that's what's going on here. Confusingly, the h is representing the width of a trapezoid. So we have our endpoints a, b, and the number of trapezoids n. H in this case is the width of a trapezoid, and we can calculate that by finding the difference between b and a, and then dividing that by n. So now we have the width of a single trapezoid. Approx is going to be the approximate area, and we set that to be f of a plus f of b, and then all divided by 2. We're not going to multiply by h yet, because we're actually going to do that at the end. And then for I equals 1, I less than or equal to n minus 1, I plus plus, we're gonna calculate x sub I, which corresponds to the a terms in the drawing that I had. That's going to be our starting point A plus however many h's we are from the start. How many h's are we from the start? Well, that's going to be however much I is. We pass that into f of x. We pass that into our function x, so it's going to be f of xi. We add that to a prox, and that's the for loop portion of our code. Finally, we take our approximated area and then multiply it by h, because per the calculations, you have to multiply everything by h. So that's what's going on. So all this math stuff is what this code represents, and we can just write that up as a serial program, figure out that it works. But we want to parallelize this right off the bat. So there are 4 basic steps when it comes to parallelizing a program. We want to partition the problem solution into tasks. We want to identify communication channels between tasks. We want to aggregate those tasks into composite tasks. And we want to map those tasks to cores. There are 2 types of jobs that we have to do with this program. The first one is computing the area of the trapezoids, and the second one is adding the areas of the trapezoids. Here's the thing. Doesn't matter how many trapezoids we have, but does calculating the area of trapezoid A affect the area of trapezoid B? No, it shouldn't. So there is no need for communication between one thread and another when it comes to calculating one trapezoid after another. But we do need to communicate that information when it comes to adding trapezoids together. We're also going to assume that we have more trapezoids than we have threads. So we are just going to divide the work between however many threads we have. So if we have, say, 1,000 trapezoids, if we are estimating the area if we're using 1,000 trapezoids to estimate the area, and we have a 10 thread team, we're just gonna give each thread a contiguous block of 100 trapezoids. Each one is going to calculate 100 trapezoids, and then they're each gonna calculate their own local area, and then they're gonna have to and then finally the program is gonna have to compute the total area by adding those 10 different areas together. Though at the start, we're just gonna calculate each trapezoid area one by one, and then add each one to the global sum, because we're gonna have a global sum like what we did with the pi estimating program. So the code for that would look something like this. We have a trap function, which takes in 4 things. A, B, and N. A and B are the endpoints for which we are finding the area. N is the number of trapezoids, and global result, that's going to be a pointer to the global result. So you would run this program passing in as a command line argument the number of threads you wish to run this program with. We could modify this such that we can also pass in not just the thread count, but also A, B, and N. That is an option you can do, so that would require having to pass in 4 things at once, which is going to be a little bit difficult. But you can do it if you wanted to. The point is, we need to, either way, you're going to have to pass in A, B, and N. In this case, we're just going to pass in, as a command line argument, the thread count. And then, when the program runs, you're going to have to enter A, B, and N, one after another. Once the program has that information, it's going to call the trap function, passing in A, B, and N, and an address to the global result. And all that is going to be part of a parallel section. Hence this pragma directive here. Pragma OMP parallel num threads thread count. And once that is done, the program is going to print out with n equals %d trapezoids our estimate of the integral from %f to %f equals %f. Oh, by the way, this isn't the whole program. That's just the first half of it. The second half is this trap function and also our function f. We did not define what f is, but for the sake of simplicity, we're just gonna define it to be f of x equals x squared. So it's a simple quadratic. So now we have all this code, which has about the same complexity as the PySMing program we had using pthreads, where each thread had a local starting point, a local stopping point, and a local number of things to add. Or I guess a local number of things to do. Unlike the pthreads programs that we've made, we don't need to pass in a rank or a thread count. Rather, those two are just handled by OpenMP's helper functions OMP get thread num and OMP get num threads. But the idea is still the same. We have each thread calculating a contiguous portion of trapezoids, and then each thread is going to increment the global result by each trapezoid found. Okay, so let's look at the code for this. So here it's set up such that we're just gonna calculate a local result called my result. We're gonna initialize that to be f of local A plus f of local B, all divided by 2. We're gonna increment my result by f of x, where x is going to be local A plus some number of widths away from endpoint A. So we have this local my result, and then we multiply that by h. But at the end, we need to add that to the global result. And that's where things would pose an issue, because if each thread is adding to the global result, that's a potential for a race condition. But hey, OpenMP has a directive that we can use to declare a critical section. So, remember back with pthreads we had to create and destroy a lock? And not just that, we had to call lock and unlock before and after we enter a critical section. We don't have to do that here. Instead, we just add in this directive, pragma OMP critical, and that's a critical section right there. No need to hard code a lock. Rather, the compiler does all that work for us. By the way, the code that I have here is specific for a Windows system. If on a Unix system, you might want to swap out scanf s for scanf, even though that might not be advised. It might not be advised to use scanf due to security reasons. Let's quickly talk about the scope of variables. Think of the scope as the region between curly brackets in which a variable can be used. So you have some variable that you define, and then after it's defined, you can use it literally anywhere within the program that is bound by the curly brackets. So you can't use a variable before you define it, because the compiler will basically say, I have no idea what this is. This variable is undefined. But you can use it after you define it. If there's another region of curly brackets if you have another region of curly brackets, you can use that same variable in there, unless you have some other variable with the same name. Then it's going to be that variable that's going to be used instead. So scope and curly brackets only works. So the idea of thinking of scope as the region bounded by curly brackets, that only works if your programming language has curly brackets to begin with. It's a little bit different if you are working with, say, Python, Rather, it's the indent levels that define scope. But since we're dealing with C, or you might be working with C++ instead, but either way, it's going to be defined. Scope is defined by the region bounded by the curly brackets. If you define a variable outside the curly brackets, you might have a variable with global scope. If you've ever defined a global variable before, it's going to be some variable that is outside any region of curly brackets. So that's a variable with global scope. If you have a variable that is defined as part of a function, that variable has function level scope. If it's outside, you have file-wide scope. With OpenMP, you can either have variables that only a single thread can access, so that's private scope, or you might have variables that multiple threads can access, so that's shared scope. So, for our next programming assignment, we're going to write the same program a few different ways and show that it's basically giving the same result because, well, there are multiple different ways to program the same thing. So, the next method starts to get into what is called a reduction clause. But let's talk about the alternative, the first alternative that we have here. So, we have our first implementation is a void function that accesses the global result using a pointer. But rather, another way would be to redefine this trap function so it returns a double. So instead of passing 3 things plus a pointer, we would just passing 3 things and this function would return a double. And our function call would be global result equals trap ABN. Our trap function would then have the following changes. As I said, instead of just 4 things where one of them is a pointer, there are only now 3 things that we have to pass in. Here there is no more critical section, and now the trap function returns my result. Each thread returns its part of the calculation in the form of its my result variable. So each thread has its own local version of my result. So my result is private scope. Well, as is my rank and thread count, even though thread count is going to be the same for every thread. But this poses a problem with how we have to call this trap function. So now we have this pragma OMP parallel. So we still have the parallel section in the main function, but now we have to move the critical section to the main function within the parallel section. So pragma OMP parallel num threads thread count, but inside that we have pragma OMP critical. And then as part of the critical section, we are incrementing the global result by the trap function. So every thread is calling the trap function. But the problem with this is, because of how this is coded, it may result in the trap function being called by each thread, but by one thread at a time. So that's a problem. The past times I've ran this program, I could not get a speed difference, but it might be the case that you might get a slowdown, because if you do get a slowdown, it's because the trap function is being called one thread at a time, when we ideally want the trap function to be called by every thread. But because we have defined this line of code as a critical section, we're calling trap is being called by one thread at a time. So how do we fix that? Well, we can rewrite it as follows. So my result equals 0. So now we have defined another variable that each thread is going to have private access to. We are going to increment that by the return value of trap. So however long this thread takes to execute the trap function. Once that's done, well, at this point in the execution, every thread should be running the trap function now. It's only when we get to the critical section that we have to increment global result one thread at a time. But hey, most of the calculation's done, so in theory, this should result in a speed up in our program. So that's the fix that we have to make here. So we can write our code this way as well. But OpenMP has yet another trick that we can use. And have you ever heard of a reduction operation and a reduction variable? Chances are you've seen this before, but you've never had it shown to you. A reduction operation is an associative binary operation, and reduction is a computation in which we apply to some reduction variable the same reduction operation over and over and over again. The simplest example I can think of is you have an array full of numbers and you want to add all the numbers in that array into some sum. So we are incrementing the sum by I, where I is defined by this for loop over here. So we are incrementing the sum by some amount from our array. In this case, the sum is our reduction variable, and addition is our reduction operation. OpenMP lets us define a reduction operation using what is called the reduction clause. So let me go back a few slides. Here, we have the global result being added to over and over and over again, but in this case, each thread is adding to the global result. But that still counts as a reduction operation, because trap is set up such that each thread is going to calculate its portion of trapezoids and then add its local result to the global result. This still counts as a reduction operation because we're adding to the global result by each thread's local myResult. And myResult is defined by our trap function, or rather, it's the return value of our trap function. So we are adding to global result over and over and over again using addition. Therefore, global result is our reduction variable, addition is our reduction operation. So if you want to define this if you want to rewrite this section of code using a reduction clause, here we go. So now we have condensed our two directives into just one directive now. Now the code looks no different than if this was serial code. By the way, here's the syntax for a reduction clause. Reduction, left parenthesis, reduction operator, colon, and then your reduction variables, and then right parenthesis. Reduction operations include addition, subtraction, multiplication, bitwise and, or, and XOR, and logical and logical OR. There you go. Shown on the right, it's at the bottom. So much like our pi estimating program, we should then get the same result no matter what. You're still seeing different results. That might be because of floating point arithmetic not being associative. So that is what we're going to do for our next programming assignment. And this leads into yet another way we can write our program using what is called the parallel for directive. I'll get into that a little bit later, but let's look at, well, coding this thing now. So I'm back in my virtual machine right now, so I'm just gonna make a copy of the Hello World program, and I'm just gonna call it OpenMP Trap 1. Actually, no, I'm not gonna call it that. Rather, I'm just gonna call it Trap 1, There we go. Open that, and most of the code is going to be the same. Well, no, only the boilerplate code is going to be the same. So let me just delete all of this and all of that. And we will need two function prototypes for this. And that is, the first one is for the trap function itself. And this is the function that calculates the area of all our trapezoids. So it has 4 things being passed in. The first 2 are doubles, the third one is an int, and the last thing is a pointer to a double. And of course you have to define f of x. We're just gonna call that function f. Okay, so the skeleton of our code is there, but now we need to add the rest of our variables. Excuse me. So A and B are our leftmost and rightmost endpoints. Global result is, well, just a result. And it's just the number of trapezoids. Oh yeah, we also need the thread count, because we are specifying the thread count ourselves. So we're going to get the thread count as a command line argument. So thread count equals strtol argv1, comma, null, comma, 10, because this is just going to be a base 10 number. Next, the user is going to be prompted to enter A, B, and N. So we can be as simple or as descriptive as we want here. And then we're gonna use scan f, and then we're gonna type in %lf. No commas here, so it's going to be one number after another, but we are spacing them out with, well, a single space in between each one. So %lf, %lf, %d, and then we're gonna pass in address A. There we go. Address A, address B, address N. So in this parallel section that we're now gonna write, each thread is going to calculate its own portion of trapezoids. And the number of threads we're going to use is going to be defined by whatever we passed in as a command line argument up here. This is just a simple function call where we pass in A, B, and N, and the address of the global result. There we go. And now we can just print out the final result. Okay. And there we go. Okay, but we still have to write, still have to implement the trap function and the f function. So and the function is of course going to be in the PowerPoint slides as well. So I'll just put that on my side monitor while I go about and code the rest of it. Yeah, so the meat and potatoes of your program is the trap function itself. So we're just gonna pass in. Yeah, I'm just gonna copy this part here and paste it down here. Okay. Remember that h is the width of a single trapezoid, confusingly. X is going to be the height of a single trapezoid. And my result is just the local result for a single thread's portion of trapezoids. Yes, I'll have a local A and a local B. Those are the threads starting and stopping points for its area, for its own local area. So it would probably be a good idea to comment these. Maybe it's better to write it like this, so. So the next variable I, that's just going to be used for the for loop, and local n, that's just the thread's local number of trapezoids. And as I said, unlike p-threads where we had to define a global variable for the thread count and we had to pass in the rank, we just have OMP get thread num and OMP get num threads to get us the rank and thread count. So my rank equals OMP get thread num and thread count equals OMP get num threads. There we go. Let's calculate the width of a single trapezoid. H equals B minus A all divided by N. So local N equals N divided by thread count. So N is the number of trapezoids, but N over thread count, that is however many trapezoids the thread is going to calculate. We're gonna also calculate local A and local B. So local A is A plus my rank plus A plus my rank, but also it's going to be A plus my rank times local N times H. Local B is local A plus local N times H, and we're gonna initialize my result to be, my result equals F of local A plus F of local B all divided by 2.0. And it must be divided by 2.0 because the compiler will interpret that as floating point division. If we just did divide by 2 but not have 2.0, that's just going to be interpreted as integer division, even though it probably should be okay if we just have, it should be okay if we write it even as divide by 2 instead of divide by 2.0, but I have it written as 2.0 just to be absolutely sure that this is supposed to be integer division. So the function f should return floating point variables, which the compiler should understand to mean floating point division. I'll just write it as 2.0. Just, I guess it's for my convenience as a programmer. But anyway. So now we're gonna add all the other trapezoids. So for we already defined I, so I don't have to say I equals whatever. I just have to say I equals. We're gonna start at 1. And then I is less than or equal to local N minus 1. And then I plus plus. We don't have to calculate the height. We don't have to calculate 2 heights for a trapezoid because previously I showed you why it is the case that we just have to calculate 1 height. It's just a means of rearranging all the terms so that instead of calculating half of 2 different heights over and over and over again, we just have to calculate 1 height and that's it. So first I have to calculate x, that is going to be local A plus I times h. And then we just pass that into f of x and increment my result by that amount. Remember, everything is being multiplied by h, where h is the width of a single trapezoid. Okay, so this next part is going to be our critical section. So pragma, be critical, and then I guess if I want to make it clear that this is supposed to be a critical section, even though it's just one line, I'm just going to enclose this block of code with curly brackets anyway. So that's our function for calculating the area. But now we have to we need the function for f of x itself. So just define f of x to be f of x equals f squared. There we go. So that should be our whole program now. Okay. Open in terminal and the gcc -g -wall -f open mp -o. The name of our program is trap1, and the source code file is trap1.c. There we go, it compiled. So now let's run it. It segfaulted because I did not enter the number of threads. Let's do that again. Okay. Enter endpoints A and B followed by the number of trapezoids. Let's do endpoints 0 and 10. And let's do 1,000 trapezoids. That means each thread is doing 100 trapezoids each. And we have an approximate area of 333.3335. Which means if we do this again with 0, 10, and even more trapezoids, let's do that many, it gets an even more accurate result of 333.333. So that's telling us it's supposed to be 333 and 1/3. Okay, so the first programming portion of your assignment is to implement the trapezoidal rule program as follows. Enter and solve the code. The next portion has you use the next version of this program has you modify the trap function such that instead of having to pass in 4 things, we only have to pass in 3 things, and the trap function now returns a value. Let's call this one trap2. And now let's modify this right now. So instead of passing in 4 things, we're passing in 3 things, and the trap function now returns a double. The function call for this should now have the trap function no longer have a global result be passed in. Instead, we are incrementing the global result by the return value of our trap function. And because this is a parallel section in which each function call is done by a separate thread, we need to add in that directive that defines a parallel section. So there we go. So now we have to modify this trap function accordingly. So the return type is no longer void, it's double. We don't need this fourth parameter here. We can take that out. We don't need the critical section in the trap function anymore because the critical section is in the main function now. So now, all I gotta do is return. Okay, so everything up until this point is the program, or rather this single function, calculating my result. But since we no longer have a pointer to the global result passed in anymore, we're just gonna return my result. So these are very minuscule changes compared to our program. But let's see whether that gives us the same result as before. Enter endpoints A and B followed by the number of trapezoids, 0, 10, and let's do 1 million trapezoids. We're still getting the same result as before. But the problem is, because that critical section contained a function call, that potentially means instead of each thread calling trap at once, each thread must wait its turn to call trap. That's not good. So we're gonna rewrite this program a third way. Open that up. So this is going to require rather minuscule changes to our parallel section here. I'm going to cut that out, and I'm going to say double my result equals 0.0, and then my result plus equals trap ABN. And then I'm gonna say global result plus equals my result. So now the increment operation here, the right hand side is just a variable, not a function call. We already did the function call before we entered the critical section. So in theory, this should result in faster execution because now each thread is free to call trap without having to wait for its turn. They will need to wait for its turn to add to the global result, but that should be far less waiting than waiting for your turn to execute the trap function. I say trap function when in operating systems, trap is something else. But notice that we don't have to do anything to the trap function itself. It's only the changes that we had to do here. So now it's starting to look like we have a reduction operation now. We'll get to that in a little bit, but I want to now compile this program now. There we go. I am now gonna call this, I'm gonna run this with 10 threads as before. Endpoints 0, 10, and 1 million trapezoids. There we go. Same result as before. It's working. Alright, the last implementation is to rewrite this once more. But instead of having to write all this, we're just gonna add that reduction clause, because we are adding to the result over and over and over again, or rather, the global result is being added to by each thread. So we can just turn that into a reduction operation as follows. So this, okay, it's already a reduction operation, but we're gonna tell the compiler, okay, this is part of a reduction operation, let's just parallelize the whole reduction operation. So our reduction operation is addition, and the reduction variable is result, global result. There we go. So now what we can do is condense all this code back to just this global result plus equals trap abn. It's the compiler that has to worry about. Okay, so we wrote this as though this was serial code. But now it's the compiler that's going to convert that into the suitable parallel code. How neat is that? This is what makes OpenMP so powerful. It takes barely any modifications to our code just to make it parallel. In fact, I could probably gut all of this and turn it into a serial program and just add in back the directives to turn it back into a parallel program. Of course, there's still all this we have to contend with. Each thread must calculate its own starting and stopping point, but we can obviate the need for all of this boilerplate code when we get to the parallel for directive, because using that, it's as though we're just writing serial code and then telling the compiler, okay, I want to turn this into a parallel equivalent code, and it's going to be on the compiler's part to, well, convert for us. The only other additions that we might have to do has to do with whether we need to work with line rank and thread count. But other than those additions, it's as though we're writing serial code. So now this program should work the same way as the last three programs did. So this is the fourth version of the same exact program. Let's try it now. So I'm going to recompile this program once more. There we go. I am going to run it with 10 threads, endpoint 0, 10, and 1 million. There we go. Same result. It works the same as before. It might be worthwhile to time it might be worthwhile to check whether each different version is running at the same time, at the same amount of time, or a different amount of time. But I'm not requiring that because in my testing, sometimes I found no differing results. So this is just a step-by-step process of building up a program, trying out some things from OpenMP, and then rewriting it using those methods, and realizing we don't need to do anything special to turn our program into a parallel program. All you really need to know for the most part are those directives. So that is going to be it for the programming portion. I am going to talk about what the parallel for directive is like real quick. So this next part is going to be part of your next programming assignment, where we're going to use the parallel for directive to simplify our program even more. So this is our program. Well, actually, this is the serial version of our program. Strangely enough, I did not have you start with writing a serial version of your program, but next up, we are going to write the serial version of our program and then turn it into a parallel program by just adding a single directive to it. That's it. This is going to use everything we know so far. That includes the reduction operation. By using a reduction operation, we obviate the need for having a critical section. And that's it! So, let me talk about the details of the parallel for directive really quick. By default, when we add the parallel for directive, basically it does all the work of calculating. Basically, it abstracts away the work of having to calculate each thread's starting and stopping location. Basically, it partitions the work of our for loop such that for m partitions and a thread count t, the first thread gets the first m over t partitions, the next thread gets the next m over t partitions, and so on. There are a few caveats to this, however. 1, you cannot parallelize an infinite loop. 2, you cannot parallelize a for loop where the number of iterations cannot be determined. Also, you cannot parallelize a for loop if that loop contains a break. Because in the latter two cases, we cannot determine the number of iterations. Basically, the parallel for directive only works if you know that the number of iterations is not going to change. If you know how many for loop iterations you're going to have, you can use the parallel for directive. Basically, OpenMP can only parallelize for loops that are in a canonical form. So the first part is, so index is going to correspond to the I variable in a for loop, like for int I equals 0, index it corresponds to I. Your index is going to have a definite starting position. Your index is also going to have a definite end position, and your index is going to be incremented consistently. So it's going to be plus plus, or minus minus, or some increment amount. Also, the expression start index and end must be of a compatible type, and none of this can change during the execution of the loop. And the variable index can only be modified in the increment step of your for loop. So the increment expression, these are the only increment operations that are allowed. You cannot increment the index anywhere else in your for loop. This is the only place where you're allowed to increment. And if your for loop fails to meet any of those conditions, your compiler will just reject the for loop. Like, a linear search is a good example of a parallel for loop that OpenMP, or rather the compiler, will fail to compile. Because linear search is basically like going through a list one element by element at a time until you find your result. Where are you going to find your result? You won't know where to begin with. You won't know where it ends. Well, you know where you're going to start, but you don't know where it's going to end. Therefore, parallel for directive only works if you know where you're going to start and you know where you're going to end. But this linear search function here is set up such that if it finds a result, it's going to break immediately. Or rather, it's going to return immediately. This kind of setup is going to throw an error if you try to compile it. Oh, by the way, there is another case in which you would not want to parallelize a for loop. There is something called a data dependency, where the result of one for loop iteration is required for the next for loop iteration. Consider the example of the Fibonacci numbers. 1, 1, 2, 3, 5, 8, 13, and so on. You cannot calculate the nth Fibonacci number without having first calculated all the Fibonacci numbers before that. This is called a loop carry dependence, and yeah, you can try to parallelize a for loop in this way, but you're not going to get a good result. You're going to get a garbage result. something like, okay. So, really, you just need to be aware of two things. What forms of a for loop you are allowed to parallelize using the parallel for directive, and also being aware of any loop carry dependencies where the for loop requires the result of the previous iterations to calculate the next iteration. Something like this has a data dependence, but none of this requires anything from the last for loop iteration. If we have I and then I and then I in here, this is okay. But if you have I, but also an I minus 1, no good. No bueno. This is not an example of a loop carry dependence because, well, at no point in this calculation are we requiring anything from the previous iteration. So we're going to try our hand at the parallel for directive next week. Okay, so that's going to be it for this video. If you have any questions, let me know. Good luck on the assignment.